Continuity at a point, you guys. The first page, there isn't much to put on the first page. A continuous curve is any function that can be sketched in one motion. So, we don't really study continuous curves. That's algebra 1. This is a continuous curve. You don't have to do this. A diagonal line, a parabola. Those are all continuous curves, right? We study a lot of discontinuous graphs, and this is what they look like.
We stalled for a while.
I probably would have made it here. I don't know why.
Things like that, right? Where you have to, discontinuous breaks in your graph, and that's what we study in here. So we're going to study continuity. We're really studying discontinuity. Where does it not, where does it break is what we're going to study today. We are done with page 1.
Guess not.
Okay, continuity. Discontinuity, yes, sorry. So this is exactly out of the book. I just kind of recopied it. Some of you only read the exercises page, and you don't read the pages before the exercises. There are other pages in a math book, so it wouldn't be a bad idea to start looking over those. But a removable continuity, discontinuity, a point in which a graph is not connected, this one or this one, these are exactly out of the book. It's not connected, but the limit of the function exists. They're not connected, but does the limit exist at 0 or 1? 0, it does exist here. 1 exists there. But the limit of the function exists, but does not equal the value of the function at that point. Both of those are called removable discontinuity. So let's talk about these again. We already know that the limit exists at 0, and we already know that the limit exists at 1. Does everybody understand that so far? But it does not equal the value of the function at that point. So if I asked you the limit as x approaches 0 of this f of x, this equals, let's just put this at 1. Everybody understands that? If I asked you what f of 0 was though, you guys, what's f of 0? There isn't one, right? It does not exist. The actual point from algebra does not exist. So that's called a removable discontinuity. The limit of some f of x as x approaches 1, doesn't that equal 1 for this one? But the actual point f of 1, the actual point f of 1 is equal to a negative 1, isn't it? Back in algebra. Limits and points are totally different things in math. We already got the removable discontinuity. Okay? Non-removable. This is the only removable one. There are 3 non-removable ones. Let's talk about the jump. A jump is one-sided limits exist but have different values. So this is a non-removable one right here. This is non-removable. It's called a jump because basically you're drawing this one and then you have to jump up to draw the rest of the graph, which makes sense, correct? So that's a jump. One-sided limits exist but have different values. That's an easy one, right? The next one, infinite. One-sided limits exist and have the same values but makes a vertical asymptote. So at exactly 3, x equals 3, there's an infinite discontinuity, which means you're drawing your graph, you have to take your pencil off to draw the rest of it, and in between there is a infinite discontinuity. The other one had a jump. This one has an infinite discontinuity. And the last one is an oscillating one. Don't even worry about that. It will not be on the AP test. So it will only be those 3 mainly on the AP. Oscillating, basically, I'll just explain to you. It's just a graph that just keeps oscillating back and forth, and it'll never ever get closer and closer, to one specific limit. But don't even worry about the oscillating one. It's not even on the AP test. So, okay, next one. compositions. Oh, you've never done this before. If f of x and g of x are continuous, then f of g of x and g of f of x are also continuous. The compositions, these are compositions. So let's review compositions again. Let's go up here and review what a composition is. So f of x is equal to really basic x plus 1. G of x is 2x. We're going to just review what a composition is, and then we'll talk about what this is down here, which you've never done before. If I ask you to find f of g of x, this is called a composition. We're going to find the derivative of this later, which is kind of fun in another section, but that means you take g of x, which is all of that, and you replace the x in f of x with 2x. That's called a composition. So what is f of g of x? It equals 2x plus 1. We could go the other way and do g of f of x. That means all of this, f of x, has to be put in for this x in g of x, which gives you 2 parentheses x plus 1, which gives you 2x plus 2. Two different answers. One is f of g of x and g of f of x. Do you guys remember doing compositions and algebra? Okay, this totally makes sense then. So let's talk about this. If f of x and g of x are continuous, so let's look at f of x. X plus 1, isn't that a diagonal line? All diagonal lines are continuous. G of x is also another diagonal line with a slope. Since these two are continuous, then their compositions are also have to be continuous. This is continuous, this is just another line, and this is also just another line, so it's true, isn't it? So now, you've never done this before. They're giving you h of x. H of x is equal to x plus 2 squared. This is the composition. Then what is f of x and g of x? This is the actual answer. Okay, so this is like either this one or this one. How do you go from there back to there is what you're trying to do, right? You're trying to go backwards. So what's f of x? There's different ways you can answer it, but f of x is equal to, what could you let f of x equal? X squared? Yeah. Yep, f of x is equal to x squared, so what's g of x have to equal for that to equal that? Very good. F of x is equal to x squared, g of x is equal to x plus 2. That one would be f of g of x, wouldn't it, you guys? Let's check it. F of g of x. G of x, which is x plus 2, has to go in for all the x's, which would make that, wouldn't it? So did he do it right? What's another one? You could say, I don't know what's another one. F of x is equal to, I think that's good. That's plenty. So do I have any more? Is there another one down below?
Yeah.
Is there an yeah, that's what I thought. It is, right? Yep, here's another one. If h of x, this is the composition, you guys, then what is f of x and g of x? What could f of x equal? And what could g of x equal?
F of x could equal the absolute value of x.
Yep.
G of x could equal x minus 30.
Very good. You've never done this before. You've never went backwards, you've always just went one way, so. I think you guys get it. You guys want another one, or you guys get it? And just check it to see if it makes sense. Do f of g of x or g of f of x, so. Oh, you have room on the top of that one. I want to talk about the IVT. So this is going to go on the top or on the bottom down here. The IVT. the intermediate value theorem. The IVT. So on the AP test, they're going to ask you to explain why the answer is the answer, and you can't just say just because I got x equals 2 and that's the answer. Sometimes you have to explain it by using mathematical terms. So here's the intermediate value theorem. A function y equals f of x. Remember, y does equal f of x. So some function f of x that is continuous on the interval a to b takes on every value between f of a and f of b. Whoa. Just got too close. This is supposed to be f of b. The intermediate value theorem says a function y is equal to f of x that is continuous on some interval a and b takes on every value between f of a and f of b. So instead of showing you using just a bunch of letters, I just want to show you using actual f of x. So some function f of x, well, equals x plus 1. Just going to show you a picture here. You put your first dot at 1, and you go up 1 and over 1, up 1 and over 1, up 1 and over 1. You have some function f of x that is continuous. Is that line continuous, you guys? Yep, that line is continuous. On some interval a and b, we can just pick an interval. Let's pick the interval 1 to 3, 1 to 4. So we have a line that's continuous, and we have an interval from 1 to 4. Here's 1, 2, 3, 4, and there's 4. So far so good. Everybody understand that part of the direction? Takes on every value between f of a and f of b. That means you can find any y value. F of a and f of b are y values. So when x is 1, can you find f of 1? Isn't it going to be 2? When x is 2, you're going to get 3. When x is 3, you're going to get 4. When x is 4, you're going to get 5. You see what this... And it doesn't have to be whole numbers. It could have been 2.2 also, right? Takes on every value between f of a and f of b. It doesn't have to be whole numbers. It can be 2.2, add 1 to it, 3.2. That's all the intermediate value theorem says, that if it's continuous, if it's continuous, there's not going to be an open circle right in the middle of your problem, right? That you can find every y value in this between 1 to 4. It's called the intermediate value theorem. So, okay, moving on. Okay, part 1. That was just kind of like the introduction, and now we have the parts. Find out where it's discontinuous, and then identify the discontinuity. So you can either graph it. You can either graph it, or you can see that at x equals a negative 2, you'll have 0 in the denominator, right? So there's going to be a discontinuity at this graph because you cannot have a negative 2 in the denominator. So when you graph this, which you would do on the test, you would graph it, and you know at a negative 2 there's something, not a negative, that's a positive 2, sorry. Put it over here, at a negative 2, and there's a dotted line, because this is what the graph looks like. That's what the graph looks like. I could take time to have you guys plug it into y1, but you guys know how to run the y1 button on your calculator, so find out where it's discontinuous at, and then identify the discontinuity. So find out where it's discontinuous at. It's definitely discontinuous at x equals a negative 2, correct? Then you have to identify the discontinuity. You have to tell me why it's discontinuous. So let's go back and just really quickly, right here, is it a removable discontinuity? Is it a non-removable discontinuity? And if it's non-removable, is there a jump in the graph? Or is there a vertical asymptote and they go on to infinite? It's the infinite one, right? Go back to this, go back to this, and there's an infinite discontinuity on this one. It's undefined or discontinuous at x equals a negative 2, and there's an infinite discontinuity in this one. Okay, the next one. This one's kind of tricky. I don't know why they're even giving you this one, but when you plug y1 equals the square root of 2x plus 3, this is what you get. At exactly a negative 1.5, at a negative, right in the middle of a negative 1 and a negative 2, it's going to make a swoosh. A radical makes a swoosh and it looks like this. Kind of a tricky one because it looks like a continuous graph, correct? But there's discontinuity from a negative infinity to a negative 1.5. From a negative infinity to a negative 1.5, there's discontinuity. There's not really a name for that because it's just it's not shaded in. I would have said that this graph is continuous though. I wouldn't have said it's discontinuous from there to there. I just would not have put that. To me, this looks like a continuous graph. This is discontinuous here. There's not a name for nothing that's there though. It's just, there's not a name for this up there in that chart. But it is continuous from a negative 1.5 to infinity. I don't think this is a good example that they had in the book because there is no name for this discontinuity. It's just part of the graph that's not shaded or made the graph of it, so. Okay, do we have, okay, this one. Good to go on this page? Okay, the next page. Again, that's all we're doing today is talking about discontinuity. Find the discontinuities. I could have wrote it all out, but I just didn't want to. Find the discontinuity, which are removable or not removable is what they're asking you to talk about. So the non-removable ones are the infinite ones and the jump one. And the removable one, it's the one where the limit exists. The limit exists, but it doesn't match up with the actual point at that spot, correct? Okay, so let's talk about f of x. Let's talk about this one. We have a couple of them to do. Okay, so this one, I like graphing them. Okay, I'm gonna have you guys, we have time, I'm gonna have you guys graph these so you know what you're doing. So graph y1, and under y1 do alpha f1, and plug in the 1 divided by x minus 1, and hit graph. Okay, so if you did the 1 divided by the x minus 1, it looks like this type of a graph. Yeah, that's what you have. Are you almost done? I think I'm almost there. Is that what you have? If you graph just the 1 divided by the x minus 1, it should look like that. It should look like that. Yeah, but you don't want the part, you only want the part less than x is less than 1. You only want the part x is less than 1. Well, you know, even though this $120 calculator, you know that there's a line right there at x equals 1. So the only part of the graph you want to do is this part of the graph. Don't even do the second part of the graph, but you're using this to help you draw. You only want less than 1, and that's the only part of the graph. You don't want to draw the other one. You can ignore the other one. And now I'm going to erase that one, and I'm going to plug in x to the third, x raised to the third, whoops, start again, x raised to the third minus 2x plus 5. And it looks like a snake, you guys. It looks like a snake when you do it, right? It looks like a snake, but you specifically want to start at what number? 1. And if it's hard to see what the answer is at 1, go to your second table. And at 1, it is,
4.
I'm positive, but I'm going to check it again. At 1, it's 4. So at 1, it's 1, 2, 3, 4. 1 right here. And at 2, wow, it's 9. It's way up here. And I'm going to be done. But it looks like this. It looks like this for the second part of the graph. X is greater than or equal to 1. You can have a closed dot at the 1. Okay, it's discontinuous. You know exactly where you, when you draw your graph, you always start from left to right. It goes from here, and then you have to pick it up and go like that. So it's discontinuous at, x equals 1. And this is a tricky one, because what do you call that? It looks like an infinite on one side. You know, this looks infinite on one side, but then there's the point on this side. I don't even know what you call this one. They say it's a non-removable one, but they don't give you the name of the because this is not a, I would call this, if anything, a jump. I don't know what I'd give you a jump. I'd give you the jump probably. An infinite one, it is kind of infinite because it goes down here, but the other one doesn't go to the same limit. I don't know when you have too much stuff going on in the same spot. So they just said, it doesn't come to the same place is what the book said. It doesn't give it a name at all. Which are removable or non-removable? This is definitely a non-removable one. We just don't know the name of the non-removable one. Remember the non-removable ones, you guys, are, where are they? Right here. The non-removable ones are the jumps. They're the infinite ones. So they're definitely a non-removable one going on. It's just a little bit of each, right? Yeah, okay.
Infinite and jumps.
Exactly.
So we could call it an infinite jump.
Exactly, I guess.
Yeah.
But they're not even asking you to name it. They're just asking you if it's removable or non-removable, so you can just say it's non-removable. Yeah, so, and then this one down here, we already had this one already. This is a parabola that faces down, and it starts at 1, and it looks like this. But x can't equal a -1, so at a -1 there is an open circle. We already did this one, I think, a couple sections ago. Y equals 2 at x equals a -1. At a -1, y equals 2. It's discontinuous at x equals what? Where do you have to pick up your pen and then restart your graph again at? -1. And this is a removable one. The definition of a removable one is when the limit exists at a -1. Does the limit exist at a -1? And is there a point at -1 that you would have done in algebra? Yes, the point is -1, 2. So this is called a removable one, correct? Good? Okay, moving on. Part 3, give a formula that makes f of x continuous. Give a formula that makes the f of x continuous. So right now, it's discontinuous because when you plug a -4 in there, it makes 0 in the denominator, and a lot of you go, that's right, this isn't too difficult. I'm gonna factor this to x minus 4 and x plus 4, divided by x plus 4. The x plus 4's go away. I just came up with a new f of x that makes it continuous now, right? I got rid of the part that was discontinuous. I factored out and reduced it to x minus 4, and I'm done already. I just came up with a formula that makes it now continuous. So, okay, this is really weird, but when you plug this one into the calculator, it looks like this. -4 and a -4. I don't even, there's gonna be a hole for this one, right? Because it can't happen at -4, but on this one, no, that's the wrong graph, it's the wrong graph. It's gonna look like x minus 4, it's supposed to be in this direction, the slope is like that. So this is a x minus 4. If you graph this one, why don't you guys just do it, I'll prove it to you, I don't even, so graph the first one, alpha f1, and put in x squared minus 16 divided by x plus 4. Yeah, my graph was completely, it has a positive slope, aren't you guys, I knew that. I'm glad I'd rather just graph it. It looks like this. So I did x squared minus 16 over x plus 4, and this is what it looks like, correct? And isn't f of x equals x minus 4 also look like this? Okay, but when you look at the table for this one right here, everybody go look at the table for this one, at specifically at 4, the table, it says that it's 0, but it really is undefined until you get it to the, you know what I mean? There's really an open circle at this one, and this one there's not an open circle. But so it looks like this for that one, and then this is shaded in for that one. You can see the difference between the two types of graphs, even though what this is doing is simplifying it to this one automatically. So it's making a straight graph, but there's really a discontinuous at x equals a -4 on this one, correct? Got that? Everybody see the difference between these two? This one would have a hole in it, and this one wouldn't have a hole in it.
Would it be a positive 4 or -4? The hole on the x-axis.
Oh, that's, yeah, I don't even know, yeah, you're right. You're right, it's at a -4, not at 4,
okay.
Why don't you tell me? I've really botched this up.
Gotcha.
There's an error at a -4,
Alright.
not at a +4, thank you, I am sorry. At a -4, why don't you tell me that, but that's okay. There's an error at a -4 on my calculator, sorry. I don't, yeah, just interrupt me if you see I'm going off the track. I'm supposed to be
right now, not
I'm looking at a -4, not a +4. +4 it works. When I plug a 4 in there, it makes 8. 4 is okay. I have no idea why I was looking at a +4. We're specifically looking at a -4. Okay.
Close enough.
Okay.
Close enough for you.
Yes, thank you for telling me that, Reese.
Didn't know.
I was just sitting here half asleep.
Yeah. I'm not perfect, so I never said I was perfect. Is there anything else down there, you guys?
Well, last page.
What's
Let's
this?
get it done with.
What's this?
Last page, let's go.
What?
Last page,
What
let's
is
go.
this?
Last page, let's go.
Draw a graph. Oh. Oh, okay. Yeah, let's do this one, then we'll go back to that one.
Alright.
Oh.
This is on the AP test. I've seen this exact question on the AP test. Show that the piecewise function is continuous by finding a at x equals 2. Show that the piecewise function is continuous by finding a at x equals 2. So, if it's continuous at x equals 2, you guys, and you have two different graphs, like if it goes like this, and then it shapes in, it goes like this, like these are two different graphs. If it's continuous and you don't have to keep it going, at 2, both of these have to have the same what value? Don't they have to have the same y value to be continuous? So basically, they have to be equal to each other, or they have to have the same y value, y equals. So all you do is you set 2ax equal to 4x plus 8. Because you want them to be equal at the spot that they're asking you for to be equal, for it to be continuous, right? The y values have to be equal. Or you're checking it at x equals 2, so in place of all your x's, what are you going to put in place of all your x's? 2, and what's the only, you're trying to find what letter? Variable a, so it's going to be 4a equals 8 plus 8. 4a equals 16, so a equals 4. Show that the piecewise function is continuous by finding a, and if it's continuous, you have to have the same y values if it's a continuous function. So, good to go on that one? Everybody got that one? Okay, now comes the last part. I'm going to ask you to do this one on the test. Draw a graph if f of 1 exists, but the limit of f of x as x approaches 1 does not exist. So, I'm going to have you come up and do it.
Why?
I make them every year come up and do this.
Everyone's going crazy.
So on the test, I'm going to ask you to draw a graph if f of 1 exists, the actual point exists, correct? But the limit of f of x as x approaches 1 does not exist. On the test, I'm going to give you a scenario like this, and you have to draw your own graph. Multiple answers are going to work for this, correct? So somebody come up, and I don't even know if we should.
If we can do it, I'll just sit.
I wonder if we should touch the pen though. I wonder.
Nope, I guess we can't do it. It is not color friendly.
Okay, why don't you explain to me what you want me to do? What do you want me to do at f of 1?
Alright, so
Sorry.
at the point
f of 1 exists.
yeah. My stuttering sucks.
You're good.
It's okay.
A point at
1. Yep.
1, 2,
Okay.
and opens
Can I just put it right here?
circle,
Or I'll put it right here.
yeah, and then just any line off to the left,
To the left.
and then at 1, -3,
At 1, -3.
another open circle,
Okay.
and then off to the right.
Okay. Draw a graph if f of 1 exists. F of 1 exists, yes it does, the point actually exists, but the limit doesn't exist because it doesn't come to the same road.